Hey everybody, Mr. Judson here. So this week one of our main goals is to talk about this idea of optimization. And what optimization means is how do you optimize whatever it is we're talking about. Optimize might mean to maximize the area of something. It might mean to maximize your profits as a business or your revenue. It could be to minimize your cost, okay? Or to minimize the amount of materials needed to paint the dome, Tacoma Dome. So that's what we're looking at. We're looking at how do we maximize or minimize something. And we're going to see that word show up in almost every question. What price should be charged to maximize the revenue? And if we think about it, we know how to find maximums and minimums, right? Take the derivative, set it equal to 0 because that's the slope of the tangent line. Or for a minimum, take the derivative and set it equal to 0 because that's the slope of that tangent line right there, and then solve. And I often say this, in a calculus class, whenever we're working on derivatives and they ask you to solve a problem and you don't know what to do, take the derivative, set it equal to 0, and solve. It's the best guess you can make. All right? Because that's going to happen a lot. So this is actually a problem that we had last year in pre-calculus. You might even recognize it. It says that Christmas lights cost $6 per string, and a company plans to produce 100,000 strings. However, an employee has discovered that for every 20-cent increase in the price, the company sells 2,000 fewer strings of lights. Now, you might sell fewer, but you charge more, so maybe you made more money. We're not sure yet. Okay? And so when they say what price should they charge to maximize the revenue, the question we're really asking is how many times should I increase the price by 25 cents? Okay? How many times should I do that? And so one of the things that happens with a problem like this where you're talking about raising the price and selling fewer, but how does that affect your revenue? That's the thing we want to answer is how many times should I raise the price by 25 cents? So let's work through this. So first thing I need to do is I need a variable and I need to know what it stands for. So x is going to equal the number of price increases. Okay? It's where I got to start with a problem like this. If I start anywhere else, this problem becomes very difficult. All right? And I also know that revenue equals price times quantity. We talked about that last year. If I'm going to sell 100,000 strings of lights at $6 a piece, 100,000 times 6 is 600,000, and that's the revenue. That's what came into the business. Okay? Don't confuse revenue with profit, because once you get your $600,000, you got to now pay your employees, you got to pay for the building that you're working in, you got to pay your utility bills, got to pay for the supplies. There's a lot of expenses there. At the end of the day, the profit is nowhere near the revenue. All right? So what I want to do is, if I'm trying to maximize the revenue, I need to write an expression for each of these that uses the variable x. Okay, so let's start with the price. Okay, well we know the price is $6. But we're talking about raising the price by 25 cents. We just don't know how many times we're going to do that. Right? So plus 0.25 times x. $6 times a certain number of 25-cent increases. And then what's the quantity? Well, the quantity, the number of strings of lights that we're going to produce, or sell, I guess, is 100,000. That's where we're going to start. But each time I raise the price by 25 cents, I'm going to sell 2,000 fewer strings of lights. So minus 2,000 for each of those price increases. And so now if revenue equals price times quantity, we could just say here that revenue equals 6 plus 0.25x times the quantity, which is 100,000 minus 2,000 x. So at that point, I'll stop and let you guys finish this up. Okay? What price should we charge in order to maximize the revenue? We're looking for a relative maximum now. You guys go ahead and see if you can finish it. All right. So if anyone's sitting there staring, going, I don't know what to do, Mr. Judson. You didn't listen very close to what I said earlier. If you don't know what to do, just take the derivative and set equal to 0 and solve. It might be the right thing. In this case, I think it is. I think first I want to make this equation easy to work with. You know, I could do a product rule here, but why not just FOIL it and make it easy? So my revenue is going to equal 6 times 100,000 minus 6 times 2,000, that'd be 12,000, minus 12,000 x plus 0.25 times this would be 25,000 x. And then when I multiply those two, I get a negative, let's see, that's the same as a fourth, so a fourth of that would be 500 x squared. So now my revenue equals a negative 500x squared. If I add these two together, I get 13,000x plus 600,000. And so I want to find the derivative. So the derivative of this is going to be a negative 1,000x plus 13,000. And so now what I want to do is I want to set that equal to 0 and solve. Right? So remember, I don't like the idea of just writing equals 0, but it's kind of a, people get lazy, they do that. If that said equals 0, I would move this to the other side and it would become positive. So I'd have 13,000 equals 1,000x, and then I divide by 1,000 and I get x equals 13. So does that mean I'm going to charge $13 for a string of lights? Remember, we don't want to just work through a problem and get to the end and go, okay, there it is. I want to make sure everything makes sense. But what was x? Well, x was the number of price increases, right? If this question is saying what price should you charge to maximize the revenue, well, I need to plug that 13 in right here. So P of 13 is going to equal 6 plus, let's see, 0.25 is a fourth. So a fourth of 13 is going to be 3.25. So 3.25, which means we've got $9.25. That's the price we should charge for a string of lights. Now, the next question is that a maximum or is that a minimum? I didn't really check, did I? So does that mean I have to do my first derivative test? Well, you could. I think when we look right here, we'd go, oh, it's an upside down parabola. Yeah, it's got to be a maximum. Okay, but I want to use something calculus-wise to verify that. And so what I might do is I might go back to here and say, oops. I might go back to this and say R double prime is equal to a negative 1,000. And so that means that my second derivative is always negative no matter what, which means it's concave down. So if it's concave down, then that verifies that that has to be a maximum right here. So I could say, since R double prime is less than 0, we are concave down. Concave down means our graph looks like this, so therefore that has to be a maximum. So there is a maximum revenue when the price equals $9.25. Or you could say when we charge $9.25. I don't care how we word that as long as we get the message in there. So there it is right there. So that's an optimization problem. We were trying to optimize the revenue, which means make your revenue as much as possible. That's what every business tries to do. And we think it's going to happen at that price. Okay? Let's try another one like this. All right, so this is a similar problem. It says here that a company can rent 150 river rafting boats a day if they charge $70. Experience shows that for every $10 increase, you will rent 5 fewer boats. What should the company charge to maximize their revenue? Sounds like the same problem, we're just talking about boats instead of Christmas lights. All right? You guys go ahead and try it. All right, so I'm going to start the same way I did before. I'm just going to say let's let x equal the number of price increases. And I know that revenue equals price times quantity. I feel like if you forget this and you just stop and think, it makes sense. If I sell hamburgers, I got to take the number of hamburgers I sell times the price I charge. That's how much revenue I made for that day, the money coming in. All right? So my price for this river raft is going to be $70 plus, we're going to add 10 bucks, but we're not sure how many times we're going to do that. So plus 10x. And then the quantity is going to be, 150 rafts minus 5 rafts every time I raise the price by 10 bucks. So this is my number of times I raise the price. So minus 5x. And now I could say, And now I can say revenue equals price, which is 70 plus 10x, times the quantity, which is 150 minus 5x. And so now I just need to multiply it out, take the derivative, set equal to 0, and solve. Right? Again, I can use the product rule if I want. I'm just like, let's just do the derivative one term at a time. That's the easiest way to do it. So the revenue is going to equal, what is that? 105 followed by 2 zeros. And then minus 350x plus 1500x minus 50x squared. So that means revenue is a negative 50x squared. If I put these two together, I would get a positive 1150 plus 10,500. And now I'll take the derivative. So the derivative is going to be a negative 100x plus 1,150. I now need to set that equal to 0 and solve. So if I had an equal 0 here, I'd move this to the other side. And then I'll divide by 100, and I get 11.5 equals x. So is it okay to raise the price half a time? Well, sure. If that's what's going to make the most revenue, why not? We don't have to always go up in, $10 increments? It doesn't have to be $10. If I raise the price half of one time, that'd be $5. So really, any decimal number right here is okay. All right, so now I need to find the price that would maximize the revenue, which is, let's see, my price is going to be 70 plus 10 times 11.5. So that'd be 115. And then if I add those, I get 185. So we should rent this boat for $185 a day as opposed to 70 bucks a day. I mean, obviously you make a lot more money because you're renting the boats for more, but you know, something else that doesn't happen, and being a river rafting guide, I know this, when you rent out boats, people crash them into rocks all day long. Now you're not renting as many boats, you're getting more money for it, and you don't have as many people trashing your boats, crashing into rocks and things. So it's a win-win scenario. All right, if this question would have said find the revenue, well then I need to take 185 and plug it back into this function. Then I would know what my revenue is, right? They didn't ask us that. They just said what price would you charge to maximize the revenue. So, you know, again, I want to just verify that it is a relative maximum, not a minimum, because so far all I do is take the derivative and set it equal to 0. That could be a relative maximum or minimum. So R double prime is going to equal to negative 100. Therefore, we are concave down, which means our graph goes like this. And therefore, there is a maximum at 11.5. Okay. So revenue is maximized when the price equals $185. All right, let's try something different. All right, so here's another one. Again, from last year in pre-calc. An open box is to be made from a piece of cardboard that is 24 by 32 inches. What size corners should be cut away to maximize the volume? So, I don't know if you guys remember this, but we said last year if you've got a piece of cardboard like this, this is 24 inches, this is 32 inches. And what I want to do is I want to cut away the corners. And once I cut those away, I want to fold these edges up to form an open box. And so that open box would look something like this. What we did last year was we just found an equation and graphed it, and then used our calculators to find a relative maximum. Right? We didn't do any derivatives, but now we want to be able to solve this without having to graph it on the calculator. So one thing that's really important here is whatever it is we're trying to maximize or minimize, we're trying to maximize the volume. That's what you want to take the derivative of. Right? In two previous problems, we were trying to maximize the revenue. So we took the derivative of our revenue function. Right? So let's see, I need to figure out, first of all, we don't know what size squares we're cutting away. So we'll just call it x by x all the way around. And so if I want to know what the length of this side is, that means when I fold this up, what's that length right there? Well, it's 32 minus 2x, because there's an x on each side here, right? So 32 minus 2x. And when I fold this edge up, that's this piece right here. So what's the length from this point right here to this point? Well, 24 minus 2x. And then what's the height of the box? Well, when I fold that up, that x right there is the height. So if I want to find the volume of this box, I got to think length times width times height. So the volume equals 32 minus 2x times 24 minus 2x times x. All right, you guys go ahead and see if you can find the x value that would maximize the volume. All right, so if I multiply this out, here's 32 times 24, so 768. So I'm going to get 768 minus 64x minus 48x plus 4x squared. Still going to multiply that whole thing times x. And so I'm going to go ahead and multiply here first. I'm going to get 4x cubed minus 112x times x, so that'd be minus 112x squared, and then plus 768x. So now I need to take the derivative, set it equal to 0, and solve. So v prime is going to be 12x squared minus 224x plus 768. And I want to set that equal to 0 and solve. Okay, so I'm going to be lazy here, you guys. Set it equal to 0 and solve. This is not something that I want to try and factor. So I think in order to solve that, I need to go straight to the quadratic formula and say x equals a negative b plus or minus the square root of b squared, don't know what that is, minus 4 times ac, so times 12 times 768, all over 2a. And so yeah, there's a lot of stuff going on there. I'm just going to let the calculator do it for me. So I've got my numerator, which I'm going to put it in parentheses. So I've got that set of parentheses right there. And I've got 224 plus the square root of 224 squared minus 4 times 12, that's 48, times 768. There's a parenthesis to end the square root, and I need one more to end the numerator. And then divide that by 24. There we go, 14.141. That's only one of the answers. See, I did the addition part. I got to go find the other answer as well. So if I go back to my calculator, you guys may not remember this, second enter brings that whole thing back so you don't have to punch it all in again. And I just want to go up and change that to a subtraction sign. So 4.526. So remember, when we set our derivative equal to 0 and solve, we're saying that's where there's a horizontal tangent. So one of these is going to be a spot where we are maximizing the volume. The other one, we're minimizing the volume. Right? If you think of what a cubic looks like when you graph it, it looks something like this. Okay, do I want to find the maximum or do I want to find the minimum? We're trying to maximize the volume. Now on top of that, I don't even think I could cut away. See, the largest amount you can cut away from each side is half of this, which would be 12 and 12. You can't cut 14 inches away from each side. So I feel like I already know what the answer is, but I have to justify it with calculus. Okay? So I'm going to go over here and say v double prime is, if I take the derivative of this, I get 24x minus 224. And if I do v double prime at 4.526, so if I plug that in here and multiply, let's just do that on the calculator. So I'm going to take that number times 24, and then I'm going to subtract 224. So that number times 24, and then subtract 224. And I got a negative result. So what I'm going to do is I'm just going to say this is less than 0, which means we are concave down, right? We're thinking about our second derivative test. I took the second derivative, I'm plugging that number. See, I'm not setting this equal to 0 to find the critical numbers. I'm just saying, am I concave down or concave up right here? I already know the graph looks like, I guess I didn't need to move that. I already know the graph looks like this. There's a horizontal tangent here that equals 0, and there's also one here. Right? That's these two points. Okay? But this is the one that's producing the maximum. I don't even think this part of the graph out here even works. I think it's outside the domain of the problem. So all I really want to know is, at this number, am I concave down or am I concave up? So when I plug this in, I saw in the calculator I got a negative value, therefore we're concave down, which means, if we're going this way, this is a relative maximum. So there's a relative maximum at x equals 4.526. That's the amount I should cut away, the size square I should cut away from each corner. So just to make sure I give a good clear answer at the end, I want to cut 4.526 by 4.526 squares to maximize the volume. All right. Here's the thing about these optimization problems. I can show these all to you and then give you an assignment, and they're all going to be different. It's the idea that we want to make sure we get. I have to write an equation for whatever it is they're asking me to maximize or minimize. And maybe if there's other information, I'm using that to help build that equation. But I have to do that, and then I got to take the derivative and set it equal to 0 and solve, and then check to make sure that I've got either a maximum or minimum, whatever I'm looking for. Okay? Let's try one more problem, a little different. All right, so this question is asking us to find two positive numbers whose product is 132 and whose sum is a minimum. I'm trying to minimize the sum. All right? I'm not going to give you any help on this one. You guys try this one on your own. All right, so I need two numbers, and I know that they're both positive, and the product is 132. So I'm going to do this. I'm going to say that the first number equals x, and the second number equals y. And I know that the product is 132, so x times y equals 132. So if I want to get to the point where I'm just using one variable here, I could say, well, okay, then y equals 132. I'm going to move this x over and divide, and I could put that in place of this right here. So 132 over x. There's my two expressions for the numbers. Okay, they both are using the same variable, which is helpful. And now what I want to do is I want to minimize the sum. So the sum is going to equal x plus the second number, 132, divided by x. And so now to minimize that, I want to take the derivative, set it equal to 0, and solve. All right, so that means s prime, I don't like the variable s, equals, let's see, first of all, let's say that this is x plus 132 times x to the negative 1. So my derivative is going to be 1. Multiply here, you get negative 132. Subtract 1 from the exponent, you get x to the negative 2. And I want to set that equal to 0 and solve. So I'll move this to the other side, and I'll get 1 equals 132 over x squared. I'll then bring this over, so I've got x squared equals 132. And now I need to take the square root of that. So x equals root 132, which if I simplify that, let's see, that's going to be 2 times 66, which would be 2 times 33. That's going to be 2 root 33, right? There's my number. And so if I go back over here, what we're saying is this number is 2 root 33, and this one's going to be 132 divided by 2 root 33, which if I divide by 2, I would get 66 over root 33, which would be 66 root 33 over 33, which would be 2 root 33. Oh, the same number. Now I haven't verified that this is a minimum yet, right? Remember, I got to do that. For all I know, I just found the number that would maximize the sum. So I just need to run my second derivative test real quick. So let's see, I'm going to go back to this right here and say s double prime. Derivative, that's going to be 1 or 0. When I multiply here, I'm going to get a positive 264 times x to the negative third. And so s double prime equals 264 over x cubed. If I take that number, which is a positive number, and I plug it into this, we're saying s double prime of 2 root 33. It's a positive divided by a positive, which is positive, so it's got to be greater than 0. So therefore we are concave up, right? I plug into my second derivative, I get a positive answer, I'm concave up. And if I'm concave up, that must mean there's a relative minimum at that point. So all this right here is just a real quick justification that that's the answer that I want. It's a minimum, not a maximum. All right? So now I can answer my question. The two numbers are 2 root 33 and 2 root 33. There's my answer to that problem. All right, there it is. Let me get you guys a homework assignment. All right, so we're now on week 16, so assignment number 16. Monday's piece, we're doing page 224. We're going to do 3, 6, 7, 11, 13, and 19. All right, you guys, there it is. That's all we have for today. You guys take care, stay safe.